So in this lesson, we're going to go ahead and do some review of some of the concepts at the start of math structure, specifically the definition of a prime number, divisibility, and the Euclidean algorithm. So let's go ahead and get started. So we're going to start off with a couple definitions. So we're going to say that if we're given two integers, a and d, we say that d divides a if there exists some integer q such that a can be written as q times d. And so here, whenever we write d and then this bar slash over here, this will be d divides a. And then in this setting, we also say that d is a factor of a. And in the same manner, we can also say that q is a factor of a. And when d does not divide a, we'll just simply write d does not divide a. So as an example, we can look at 19. It divides 57, and so does 3, as both of them are factors, because we can write 3 times 19 is equal to 57. And in the case of 0, we have that every integer d divides 0, since we can always write 0 is equal to 0 times any integer. And so this definition says that now every integer divides 0. So 57 actually has a funny story attached to it. So it's in the mathematics community called the Grothendieck prime. So Alexander Grothendieck is maybe one of the best mathematicians who have lived in the 1900s. He developed the branch of algebraic geometry, and the tools that were developed in algebraic geometry went on to give the ideas and theory necessary to prove Fermat's theorem, which we will be covering in detail throughout this course. But Grothendieck was notorious for being an abstract thinker. He never was one to think about things concretely or work with examples. He was more of the big picture, going for like just a full-on theory, to the point that one of his students, Deline, and him had a falling out because Deline decided to apply the methods that he was doing in algebraic geometry to number theory. And in his view, Deline was better suited to just continue abstracting and generalizing. And so the story that is attached to Grothendieck in the number 57 goes to a conference that he attended where he was giving a talk, and what he was talking about was going over everyone's head. And finally someone asked him if he can make an example to maybe do a concrete example of a concrete prime number. And Grothendieck famously said, okay, let's go ahead and take 57 as our prime, which, as we just see it with this example, 57 is not prime. And so here is a meme of the Grothendieck prime. You want a specific prime number? How about 57? And so that is Grothendieck in a nutshell. If you go on further into the modern areas of mathematics, Grothendieck theory will be prevalent, as it's the foundations of modern number theory and algebraic geometry, of course, in its own disciplines, as he developed that notion. And so that's just a little fun story about 57. Alright, so let's move on. So let's go ahead and go to the basics. What is an even number? We know that an even number is a multiple of 2, and so in the language of divisibility, we can go ahead and say that an integer n is even if there exists an integer k such that n is equal to 2 times k. And similarly, we can say n is odd if we can write n as 2 times k plus 1. And so these are the basic definitions that we will be using for even and odd. And so we can now go ahead and use these divisibility conditions, and in the next lemma we'll prove a statement about even and odd. So let's look at lemma 1.2.1. So as I mentioned in the last video, this lemma 3.1.2, this refers to the book statement. And so let's go ahead and use this. So we are given that a and d are natural numbers, and we are told that d divides a. So right there, so since d divides a, by definition, there exists a q in the integers such that, so this is my shorthand for such that I'll be using, such that a is equal to d times q. So where do we go from here? Well, we know that d and a are positive. So what does that say about q? Could it be negative? Well, if it were negative, D is positive, then A would have to be negative, so Q must be positive. And so we have that Q is positive. Oops. And so what we do have here is 1 is less than or equal to Q. And we now go in the same process that we did in our last lesson with the axioms of the integers. So we have our inequality, we have 1 is less than or equal to Q. We have the multiplicative property of less than. And so we know that to get A, all we have to do is multiply by D. But we know that D is positive by assumption. So now multiply by D, and we get 1 times D. So of course this is D. Is less than or equal to D times Q. But D times Q is A, and so we get our desired answer, because now we have that 1 is less than or equal to D, since it's positive, which is less than or equal to A. And so that concludes this proof. And so now we are done. Okay, let's go ahead and try another one. So here we have an integer n, and we want to prove that if n squared is even, that happens if and only if n is even. So proof. Now, this is a review of a concept of math structures, contrapositive. But before we do that, I want to go ahead and emphasize why we want to use contrapositive as opposed to approaching this directly. So if we approach this directly, so this is going to be a way that's not going to give us what we want right now, since we don't have the tools to go for. So, first attempt. If we try to do this directly, we could say since n squared is even, then n squared is equal to 2 times k for some integer k. Alright, but now where do we go from here? Because what we need to really use in order to proceed, we want to show that n is even, but we have that n squared is equal to 2 times k, but we have no properties of square roots or factors of a square yet. So as of this moment, we don't have the tools necessary just building on the axioms of z to go about it in this way. But we will. And actually, once we have the fundamental theorem and the results leading up to it, we can prove this directly. But now we will be in that setting, we will be assuming the results that have come up to that point. Right now, we are starting from the fundamentals. We have the axioms of z, and as a result, we are stuck. So let's go ahead and try again. So we're stuck here. So attempt 2. So we're going to do the contrapositive. And so recall that if we have a statement, P implies Q, that this is logically equivalent to not Q implies not P. So in order to prove the forward direction of the statement, so we proceed by contrapositive. So we will prove the statement. So we're doing the contrapositive, so we want to have, here is our P, n squared is even, our Q is n is even. Since we're negating, not Q would be n is not even, so n is odd. So if n is odd, then n squared is odd. And so that's what we want to prove. If we prove this, we know that since the contrapositive is logically equivalent to P implies Q, we've actually proven the forward direction. N squared is even if n is even. And this is a much easier statement to prove with what we have right now. So for example, so if n is even, So if n is even, if n is odd, then n is equal to 2k plus 1 for some integer k. But then n squared is equal to 2k plus 1 squared. So 4k squared plus 2k plus 1, which is 2k squared plus k plus 1, which is odd by definition. So here we are using the fact that here we have 2k squared plus k is going to be some integer. We can go ahead and label this q. And so we have 2q plus 1. That's our definition to be odd. And so now we have that n squared is odd by definition. Now the converse is much easier. So if n is even, so now we're assuming if n is even, then n is equal to twice times 2k for some integer k. Therefore, n squared is just going to be 4k squared, which if we want to be pedantic, we can say that this is 2 times 2k squared. And so now it's 2 times some integer. And so therefore, thus, n squared is even, which is what we wanted to prove. So now we have our desired proof and we are done. And so we are done with this lemma. So in our story about the Grothendieck prime, we're talking about prime numbers, but let's go ahead and make that notion precise. So specifically, we're going to say that a number is prime if it's a natural number greater than 1, whose only factors are 1 and b. So as a consequence, 1 is not prime. So by definition, 1 is not prime. Oops. So 1 is not prime. And then we're going to define composites numbers to be natural numbers greater than 1 that have at least one positive factor other than 1 and n. And so if it's not prime and is greater than 1, then it has to be composite. And so that's how we are defining prime and composite. And so the next theorem is one that is covered in structures. Specifically, every integer greater than 1 is either prime or a product of primes. Now, in structures, the proof goes via strong induction. And I encourage you all to revisit the proof. I've included it in the lecture notes. If you go to the proof of Theorem 1.2.3, there are two proofs included inside the lecture notes. One uses strong induction, and one uses the well ordering principle. And there's a lot of similarities between the two proofs. And the reason for that is, as we saw in the previous lesson, well ordering, strong induction are equivalent, so it comes as no surprise once we get into the habit of seeing how ordering is used, that oftentimes if we can use strong induction or induction, the well ordering principle also applies. The thing is getting comfortable with using the well ordering principle in arguments, as that is a recurring theme throughout this course. And so for that reason, I will be doing the proof in this video using the well ordering principle rather than strong induction, but I still encourage you to do comparisons between the two proofs. So let's go ahead and get started with this one. So how do we use the well ordering principle to prove this? Well, for starters, well ordering, we need a set. We need a subset of the naturals that is non-empty. So how do we go from this theorem that we want to prove to a set? And the key is using contradiction. We want to go via contradiction to tell us that we have a weird, wacky number. Specifically, a positive integer greater than 1 that is neither prime or a product of primes. And so that's our first step. So, by way of contradiction, assume that there exists some integer k, some natural number k, let me write this again. Some that there exists a natural number k greater than 1 such that k is neither prime nor composite. Prime nor a product of primes. So we have here our assumption. So we know that k exists. Now construct the following set. We're going to say that S is the set of natural numbers such that n is greater than 1, n is not prime, nor a product of primes. So by construction, we have that S is a subset of the naturals, and S is non-empty. Why? Since it's non-empty, since K is an S by our contradiction assumption. So by the word ordering principle, there must exist an M in S that is a least element. Since M is greater than 1 and is not prime, it is composite. But if it's composite and it is not prime, so that means that there exists natural numbers a and b such that m is equal to a times b with a being greater than 1 and so is b, and both of them being strictly less than m. But m is the least element of S. So in particular, a times b, a and b are not in S. But if a and b are not in S, that means that they have to be products of primes. So remember, we know that m is not a product of primes. So this here we have that now a and b must be product of primes. So a is equal to p1, p2 to some p sub n, and b is equal to some q sub 1, q sub 2 to some q sub r for pi and qj prime. So we have now our products of prime, but putting everything together implies that m, which by definition is a times b, is equal to p1, p2 to pm times the q1, q2 to qr. But now we have that m is a product of primes. So m is a product of primes. But this is a contradiction. So this means m is not an S, which is a contradiction. And so now we are done. And so we have proven our theorem. And the key thing I want to emphasize with this statement is that, as I mentioned at the start, if you go about it via strong induction, you don't have to go by contradiction, you get a direct proof. But the argument will boil down to still relying on this fact. There are factors of m, a and b, that are strictly less than m. And by strong induction, you will have that both of those are products of primes. And then you piece those together to get your induction case, to prove that the m that you want is a product of primes. And so that's how the proof will go about it, how that proof will go. And so that concludes this argument. And so we have now shown that every integer greater than 1 is either prime or is a product of primes. And as I mentioned, the goal for us is to generalize that and prove that if we have a natural number greater than 1, then n is either a prime or a product of primes. And so we will have that prime factorization of a natural number as unique up to order. Because of course we have 6, we can write that as 2 times 3, but also as 3 times 2. And so it's unique, but we have to be, we will say this phrase up to order to emphasize that we can change the order, but it's still going to be unique at the end of the day. Now, this is a statement that we take for granted, and it's easy to believe that this statement should always be true. In the integers, well, that is the case, and we will prove it. But what if we make our numbers a tiny bit bigger? So what do I mean by that? So later on in the course, we're going to be studying what are known as the Gaussian integers. So I'm going to denote this by the symbol z bracket I, and so this is read z adjoined I. Oops, I put quotes. And so here, of course, I is the square root of negative 1. And so in this ring, this is going to be a ring. The way that we write these elements are going to be of the form a plus bi, where a and b are integers. And we will go ahead and extend the notions of prime that we have covered up to this point. And composites, we can generalize these statements. But then we could ask, is a number like 2, is this still prime? And it turns out that it's not. Because in the case of 2, this is 1 plus I and 1 minus I. We have a difference of squares. So here we have 1 minus I squared, which gives us 1 minus negative 1, so we get back 2. And so 2 is not prime. What about 3? It turns out that 3 is prime. In here. But 5 is not. And in the case of 5, we have 2 plus I, 2 minus I. So what we will actually be proving later on in the course is that we can generalize the fundamental theorem of arithmetic to this set of integers, the Gaussian integers. It turns out that we can prove a similar statement, that in this new ring, the Gaussian integers, we have a way of having unique prime factorization. And mathematicians for some time believed that if you extend the properties of the integers to things that look like the integers, things like the Gaussian integers, that we will always have uniqueness of prime factorization. And that is not the case. And as Gabriel Lemay, who is a person we will cover later on in the course, learned the hard way, that statement being false led to his work completely being demolished. So Lemay proved what we will talk about next lesson, Fermat's theorem, assuming that we always had a uniqueness of prime factorization. But there are simple examples where we can see that that's not the case. Let's look at a new set. So here I'm going to have z adjoin the square root of negative 5. So here, the numbers are of the form a plus b, and then the square root of negative 5, and then here a and b are integers. So notice that in this way of writing, what we have is that every time that we put something in the brackets here, it's just a plus b, and then the element over here. This is true whenever it comes to things that are square roots. I is the square root of negative 1. If you put something like a cube root, this definition will no longer be the case, but there are ways of making these things precise, and that is covered in abstract algebra as part of its coverage of ring theory. So now, but let's focus on this here. We have this set here. It turns out that we can, just as with the Gaussian integers, extend the notions of prime numbers to this ring. And we can look at 6. So we know that 6 is 2 times 3. And it turns out that, unlike the Gaussian integers were 2 factors, we can show that 2 and 3 are primes in this ring. And so, to be precise, the word that is used in abstract algebra for prime, the generalization of it that encompasses the properties that are used for the integers, is called irreducible. So 2 and 3 are irreducible. Those are the properties analogous to primes in that realm. But we can also write 6 as 1 plus the square root of negative 5 times 1 minus the square root of negative 5, since we here have a difference of squares. And so now we have 1 minus the square root of negative 5 squared, so negative 5, which gives us back 6. But it turns out that these are also prime in that sense of irreducibility, and these two. And so now we have written 6 as a product of primes in 2 different ways, which means that uniqueness of prime factorization is not a property that we should expect to generalize to all systems of integers. And so we'll come back and make those notions more precise later in the course. So now that we have this discussion with the Gaussian integers, I want to come back to this notion of how 5 was a prime and 3 was not. And so if we continue, we can say, is 7 a prime in here? And it turns out that 7 is prime, and so is 11. But then we go to 13, we can write this as 3 plus 2i, 3 minus 2i, since now we will have 9 plus 4 once we do the difference of squares. And so what differentiates 7 and 11, 13, and 3 from 13 and 5? Well, to answer that, let's consider a few more primes, 17 and 19. And we can go all the way to 23. And so what I want you to do now is to make this connection that we have, that to write 13 and 5 as elements of the Gaussian integers as a factor really boils down to difference of squares, but specifically having elements of the form that are sums of 2 squares. So here we have 2 squared plus 1 squared. And here we have 3 squared plus 2 squared. And the reason is that in all these examples we have a plus bi, a minus bi, but this is a squared plus b squared. And so we have a sum of squares. So take a moment and work out and see if we can figure out 17, 19, and 23 if those are sums of squares. Okay, so we see that 17 is a sum of squares, 16 plus 1, but 19 and 23 are not. So what's the pattern? So we see that 5, 13, and 17, if we divide it by 4, the remainder is 1. Whereas with 3, 11, 19, and 23, if we divided them by 4, we have that the remainder is 3. And this goes back to our favorite French lawyer, who in the 1600s, early 1600s, stated the following. So the statement that we're going to be looking at that Fermat conjectured on December 25, 1640 in a letter to Mersenne is the following, which is essentially what we are looking at with 13, 17, the remainder being 1, is that if we have a prime number, then it's equal to a sum of squares, a squared plus b squared, for some natural numbers a and b, if and only if the prime, when we divide it by 4, its remainder is 1. And so this is the modular arithmetic language of congruence. P congruent to 1 mod 4 means P, when we divide by 4, its remainder is 1. And we'll come back to modular arithmetic in next Friday. We'll start talking about those modular arithmetic in more detail. So this was first conjectured in 1640. There are some textbooks that call this Fermat's Christmas theorem. But one of my gripes with teaching number theory is that we attribute so much to Fermat when he did nothing other than simply conjecture. As I mentioned in the last lesson, there's only one known proof that he ever wrote. Fermat instead devoted most of his life to write letters to well-known mathematicians and challenge them to prove things that he claimed to have proven, but never provided a proof. And always had a cop-out argument for why he was not providing it. The proof is too long, I can't contain it in this letter. The proof does not fit in the margin of my textbook. And so this was something Fermat was notorious for. However, to give credit where it's due, the statements that he wrote, 48 of them, some of which were false, the rest that were true, they motivated mathematicians for centuries to develop the machinery required to prove them. And that is very true with Fermat's theorems on sums of squares, as we will be calling it throughout the course, which was proven in 1749 by Euler. Euler, 1749. And in 1893, Richard Dedekind was able to find a new proof of this sums of squares theorem that was the connection between sums of squares and the primes in the Gaussian integers. And so what it turns out, and this is one of the beautiful aspects of number theory, if you only restrict yourself to studying just the integers at a surface level, you can't do much. But if instead you go just slightly higher, as if you were taking an elevator through the structure of mathematics, you can go high enough where you can prove statements about the integers in a newer realm in a much easier way. And so, in the case of Euler, he was restricted to the integers. And we will be going through the proof that he did. And what we will see is that it is hard to go through it in the sense of he had to develop quite some clever arguments. But then when we get to 1893 with Richard Dedekind, because now it is phrased in the language of the Gaussian integers, that proof flows much smoother. The complications are gone because now we're left to looking at what are prime numbers in the Gaussian integers. And it turns out that this theorem gives us the classification of prime numbers in this new realm. And so this is one of the motivators for number theory. Yes, you're studying the integers, but oftentimes you find yourself studying things that look like the integers, in this case the Gaussian integers, or z adjoined the square root of -5, because by going higher, you're able to see more that you could not see beforehand. And we will be seeing this throughout the course as we're going to be going into different number systems with the goal of proving statements about the integers. But at first glance, it may seem like, I thought this was number theory. Why are we not studying the integers? But then we just throw a big hammer down and we hit the theorem that we want to prove by having developed the machinery necessary. So I want to end this discussion of Fermat with a quote of Gauss, which is which really summarizes my thoughts on this, is that higher arithmetic, so this is something that Gauss wrote in 1807 with reference to Fermat and the many statements that he wrote. So higher arithmetic has this special feature that many of its most beautiful theorems may be easily discovered by induction, while any proof can be obtained with the utmost difficulty. Thus it was one of the great merits of Euler to have proved several of Fermat's theorems, which he obtained, it appears, by induction. And this is when Gauss says induction in this argument, is that Fermat, since he didn't prove any of these statements, was making deductions based on patterns. As we see, we can go 3, 5, 7, 11, 13, 17, 19, 23, and so on and so forth. And then after a while, we start to see, oh, if we can write a prime number as a sums of squares, it must be, when we divide it by 4, its remainder must be 1. Oh, theorem. No. Far, far from the truth, as we will see. So in this course, this is a statement that we are going to come back to. We will be seeing two different proofs, Euler's proof and then Richard Dedekind's proof from 1893. And so now we're going to go ahead and move on towards the ancient Greeks so that we can go ahead and build the necessary language to prove statements like the sum of squares theorem. And so our first goal is to prove the fundamental theorem of arithmetic due to Euclid, 300 before Common Era. But before doing that, we're going to first prove another result due to him, specifically the division theorem. Now, in math structures, this if you took it out of Galovich, this is called the division algorithm. And as we will see, the division algorithm is actually something else. And so we're going to cover that in our next lesson. So the division theorem is specifically the statement that if we have an integer a and a natural number b, then there exists unique integers q and r such that a is equal to b times q plus r. R is between 0 and b. It could be 0, but it cannot be. But it's strictly less than b. And so here we call r the remainder of a when divided by b. I should also mention that there will be a homework question that will have you generalize this statement. So this condition that b is a natural number can be strengthened to an integer. And so you'll be doing this case b is in z. This is homework number 9, exercise number 9 of 3.5. And so in that assignment, you will be investigating what are the conditions necessary so that we can allow a and b to both be integers. But when in the case of the naturals, it's a much simpler argument. It's the same argument, just that you have to break it up into cases for the integer, specifically b is natural, b is negative, or b is 0. So how do we prove this? So this is an example of an existence and uniqueness proof. We want to show that there exists q and r, but we also want to show that they are unique. And so we're going to go about this in 2 steps. First, prove existence, then prove uniqueness. Now, in structures, this is a theorem that is proven. And the way that it's proven is using induction. Instead, I will be providing a proof using the ordering principle, just as we saw for the result that every number greater than 1 is either prime or a product of prime. So we're going to be using the ordering principle to establish the existence portion of the theorem. Now, in the lecture notes I have provided on page 17, actually page 18. So in the lecture notes I provided on page 18, the proof that is usually covered in structures for the division theorem. Another thing is that in the textbook, there is a Naomi numerical proof analysis before the division theorem. So this is theorem 3.5.1 in the book that I highly encourage you all to look over. As one of the things about working through the proof is that here A, B, Q, and R are integers. And so everything is symbolic. But at the end of the day, these are integers. And so Naomi's numerical proof goes through and showcases what is really happening with the details of the proof when all is said and done. And that's a good technique to keep in mind, because no matter how abstract these statements get, they are statements at the end of the day about the integers. And so we can always plug in and use that to gain intuition for what is happening behind the symbols. Okay, so let's go ahead and do the existence proof. Okay, so let's go ahead, take a to be an integer, b to be a natural number, and now here's the thing, we're going to be using the well ordering principle, so that means we need a set. In the previous argument with the well ordering principle, we established a set based on a contradiction argument. In this situation, we are not going by contradiction. We're going to be approaching this directly to show existence. So what we are going to do is define a set based on a and b. And so we're fixing the integer a and the natural number b. And based on those two quantities, so in this, let me write this over here as a note. A and b are fixed. And that's crucial. We're not allowing them to be arbitrary elements anymore, but specifically two fixed numbers that are, one is an integer, one is a natural number. And now what we are going to do is look at this expression here. A is equal to bq plus r. And what we are going to do is think about that q as an x and consider a minus x times b. So x is taking the place of q. So ideally, what we want is that this then is of course going to be the desired r, but not quite, because r has to satisfy that minimal property. So we have that a minus xb. And so what's x? Well, x is just going to be any integer. And so we have this integer, but we're also going to impose another condition. X is an integer, but we also want to impose that a minus xb is greater than or equal to 0. The reason for this is we can let x be any integer, but then this here could be negative. But we are looking at the end of the day for a non-negative integer r. And so we want to remove the possibility that we have a negative. So we have this set here. So by construction, we have that this set, it's a subset of the naturals including 0. And so the next question we want to ask is this set non-empty? So is SA comma b non-empty? So let's go about this by cases. If a is greater than or equal to 0, then we can take x to be equal to negative 1 so that a minus negative 1 times b is equal to a plus b. But b is a natural number, and a is assumed to be non-negative, so this here would be positive. So there we have that, and so this here would imply that a plus b is in the set SA comma b. So we have that. If instead a is negative, then we do the following clever trick. Let's look at a plus 2ab. This is the same as a plus, so we factor out over here, we have 1 plus 2b. Oops, and I messed up that. This is the clever aspect of it. I want to have this be negative. So we have 1 minus 2ab, and then we have a times 1 minus 2 times b. And so now, with this argument, what we will have is that b, we know, is a natural number in this situation. So b is positive. So we have 1 minus a negative number here. And so this is always going to be negative. A is negative. So this is positive. But we also know that we could also take x to be 2 times a. If we plug in 2 times a into x there, that's going to be an integer, so we have an element in that set. So in other words, we have that a minus 2ab is in SA comma b, but we have exhausted the two possibilities. A is non-negative and a is negative, so therefore SA comma b is non-empty. And now, by the word ordering principle, well, to be fair, this is technically an adjustment of the word ordering principle. The generalization of word ordering principle considered in exercise 12 of 2.2. So this is going to be one of the homework problems. We have that S has a least element. And this comes to no surprise. We're using something that we have not proven yet, but you'll be proving this for homework. But what I want to emphasize is we know that the set S, A, comma, B is a subset of the naturals union 0. And the word ordering principle says if you're a subset of the naturals, the only problem here is that we may have 0. And so we're technically, this may not be a subset of the naturals because we have to put in 0, which is not a natural number. But as we can expect, we're only adding a finite number of elements here. So the least element is either going to be a natural number or it could be 0. And in the homework exercise, you'll be generalizing this by applying the ordering principle where now you're a subset of the naturals and maybe some negative numbers. And you'll be able to prove that you can also show that there is a least element in that subset. And so here we have S, A, comma, B has a least element. Okay, so let's go ahead and call the least element R. So we have, so in particular, we have the following. R is non-negative and A is equal to B times some integer x, let's call that Q, plus R for some integer Q. So what have we done? The Wall ordering principle tells us that we have an element in S, A, comma, B, and we call that element R. But that element R has to equal A minus XB for some integer x. And so now what we are doing is saying that least element, we know it's non-negative because it's a subset of the naturals union 0. We know that by definition, there must be an integer, which we have gone ahead and conveniently labeled Q. And so we know that there's some integer Q, so that A is equal to BQ plus R. And so we just, because R is equal to A minus QB. So what do we have to show? We're almost there. We have the expression, A is equal to BQ plus R, but we need to show this aspect, that 0 is less than or equal to R is less than B. We have that R is greater than or equal to 0, so we just need to show that it's less than B. And so we're going to do that by contradiction. So towards a contradiction, suppose that B is greater than, R is greater than or equal to B. And so we're going to go ahead and use this. And so now what we're going to do is show that there is an element that is less than R in the set that we constructed, S sub A comma B, which will be our contradiction. All right, so let's go ahead and do that. So now we have, by assumption, R is equal to A minus BQ. And now what we're going to do is subtract B on both sides. So if we subtract B on both sides, we have R minus B on the left. And this is now going to equal A minus BQ minus B. But then the right-hand side, we can factor a B out. And so we have Q plus 1 here. But what's the problem now? What happens? What have we just shown? Well, for starters, we have the same expression that tells us we are in S of A comma B. We have A, we have B, we have a minus. We have now that X is Q plus 1. So that's an integer. But we also know that R minus B is equal to this. And since the contradiction assumption tells us that R is greater than or equal to B, we have that now this here is going to be non-negative, which in turn tells us that R minus B is in S of A comma B, which contradicts the minimality. Of R. And now that concludes the existence portion of the proof. We still need to show uniqueness, which we are about to do. And so I want to make a few comments on this proof. It's nice, but it's very clever in the way that it's crafted. And so this is just to illustrate how the wall ordering principle can be used. But as I mentioned at the start of the proof, please look over the proof that is in the lecture notes, which does it exactly as it is done in structures via induction. So now we are going to go ahead and show uniqueness. So the way that we're going to go about this proof is we're going to assume that we can write A equals BQ plus R, but we're going to write it in two different ways, satisfying the same conclusion. And then we want to show that the Q and the R in both of them are the same. Symbolically, we have the following. So that A, Q, Q prime, R, and R prime be integers, and of course B is our natural number, such that we can write A as BQ plus R and A as BQ prime plus R prime for 0 less than or equal to R, R prime less than B. So without loss of generality, we may assume that R prime is less than or equal to R. And now what you're going to do is subtract both equations from each other. And so we're going to subtract the two equations, A equals BQ plus R, and A is equal to BQ prime plus R prime. And so that will give us A minus A equals BQ plus R minus the right hand side of the BQ prime plus R prime. So once we distribute the negative, we'll have BQ prime minus R prime. Let's go ahead and collect some of the like terms. We have BQ minus Q prime plus R minus R prime. And so we have this here. The assumption that we have that R prime is less than or equal to R implies, well, what does it imply? Well, if we look over here, we have R minus R prime. If we subtract over the R prime in this inequality, we have 0 is less than or equal to R minus R prime. So we have that R minus R prime is going to be non-negative. And so we have this statement right here. And what we want to show is uniqueness. So to show uniqueness, we want to show that R is equal to R prime. So in other words, R minus R prime is equal to 0. So that's what we want to prove. Now, we want to look at the left-hand side of the equation. We haven't looked at the A minus A, which is 0. So we now have, if we come back over here, putting everything together, we have 0 on the left-hand side. But that means that we can bring this R minus R prime over to, let's bring over the BQ minus Q prime over to the left-hand side in that equation. So doing so results in we're going to have B. There's going to be a negative from when we subtract it over, so I'm putting Q prime minus Q. I brought in the negative there. And so now this is equal to R minus R prime. So B is a factor of R minus R prime. Now, we want to show as I mentioned, so we know that r minus r prime, it suffices to show that r minus r prime is equal to 0 and q minus q prime is equal to 0, since we want to show uniqueness. We want to show that both of these are equal. So let's suppose instead that r minus r prime was positive. Now, if it's positive, lemma 1.2.1 from the last lesson will tell us, actually no, from this lesson, will tell us that because r minus r prime is positive and b is a factor, we have that 1 is less than or equal to b, which is less than or equal to r minus r prime. And so we have this statement here. But what's the problem now? We have 1 is less than or equal to b, which is less than or equal to r minus r prime. So if we come back up to this inequality over here in our initial assumptions, we have that r and r prime are less than b, but we also know that both r and r prime are non-negative. So what we have from looking at this here is that if we had subtracted on that side, may change the color. So over here, if we had subtracted, we will have that r minus r prime is less than b minus r prime, which is going to be less than b. But this is a problem, because now what we have just shown is that b is less than or equal to r minus r prime, but we know that r minus r prime is less than b by assumption. And so we have contradicted the trichotomy axiom of the integers. And so this is a contradiction. By star, which is over here. This comment that we just did over here. And so that concludes that aspect. So thus, r is equal to r prime. And it remains to show that q is equal to q prime. Well, let's go ahead and do that. We have now established that r is equal to r prime. So let's come back to this equation over here. So if we come back to this equation, let's call this double star. So by double star, we have that b times q minus q prime is equal to 0. B, by assumption, b is positive. So the zero theorem from the last lesson implies that q minus q prime is equal to 0, which implies that q is equal to q prime, which is what we wanted to show. And now we have shown uniqueness because we have shown that r is equal to r prime and q is equal to q prime. So in other words, if we have two different ways of writing this, they actually are the same exact way. And so now that establishes the division theorem. And in the next lesson, we will go ahead and see what is the Euclidean algorithm. And that will allow this theorem and the Euclidean algorithm allows us to then look at the greatest common divisor of two integers.